So we can use something called the collision model to explain how various factors affect the rate of a reaction. Just like how we can use the ideal gas model to explain the properties of a gas. So the main idea of this collision model is that in order for a reaction to occur, molecules in the reactants must collide with each other. And so just from this assumption, we can explain two factors. In an increased concentration of reactants and higher temperatures, both increase the reaction rate, because if we have increased concentration, then there are more molecules to collide with each other in the same amount of space, and at higher temperatures, those molecules are moving around faster, so they collide faster with more energy and collide more often. And so only a small fraction of the collisions between molecules actually lead to a reaction. And this is because the molecules that collide need to have a certain amount of energy, like a threshold energy called the activation energy. And so the kinetic energy from the colliding molecules is converted into potential energy, which allows the reactants, the atoms in the reactants, to rearrange themselves into the products. Remember that in a chemical reaction, the atoms in the reactants are rearranged to form the products. So that's why the colliding molecules need to have this certain amount of activation energy in order to rearrange themselves. So here we have a diagram as the reaction progresses of the potential energy of the system. So we start out with the reactants, and then when a collision occurs with the proper activation energy, the atoms are rearranged into something called the transition state. So the transition state is another arrangement of the atoms in between the reactants and the products. And so it's at the top of this sort of energy barrier, which must be overcome to get from the reactants to the products. And then after the transition state, the atoms are finished rearranging themselves into the products. And in this diagram, notice how the products are at a lower energy level than the reactants. So that means energy was released during the reaction, which means it's an exothermic reaction. So the difference between the reactants and the top of this hill is the activation energy, which must be met by the colliding molecules. And the difference in energy between the reactants and products is the total change in energy for this reaction. Another thing that affects the reaction rate is the molecular orientations. So when molecules collide, not only do they have to have the proper activation energy, but they also have to be facing a certain direction when they collide in order for the rearranging to happen. And so all of these factors affecting the reaction rate are summed up in the Arrhenius equation, which is K, the rate constant for a reaction, is equal to A, which is a constant called the frequency factor, times e to the negative activation energy over T, where is the universal gas constant in the joules form 8.314. And so if you use 8.314, then that means the activation energy in this equation is also in joules. So the frequency factor is a constant different for each particular reaction, which basically sums up all these factors, including the molecular orientations. So if we take the natural logarithm of both sides of the Arrhenius equation, then we get this new equation, ln of k equals negative activation energy over times 1 over t plus ln a. So this can be turned into a linear graph if, y is ln k, m, the slope, is negative ea over x is 1 over t, and b, the y-intercept, is ln of a. So if we graph ln of k on the y-axis and 1 over the Kelvin temperature on the x-axis, then we'll get a straight line with a slope of the negative activation energy over And so, oftentimes you want to find, let's say you have a certain temperature T1, which leads to a certain rate constant K1. And you want to know what the rate constant will be if you change the temperature to T2. So to do that, we can write the equation 2 times, once for each temperature, and then subtract the two equations. So subtract this equation from this equation, and the ln of A will cancel out, and we'll get this equation that we can use to compare the rate constants at two different temperatures without needing to know the frequency factor, because oftentimes you won't know what A is equal to. So the last thing that we're going to look at is a catalyst. And a catalyst is a substance that speeds up a reaction without actually being used up. So if we're looking at a reaction mechanism, a catalyst will not show up in the overall balanced equation, but within the mechanism itself, you'll see the catalyst being used up in one elementary step and then formed again in another elementary step. Now this is in contrast to an intermediate, which is formed in an elementary step and then used up. And so the way a catalyst speeds up a reaction is by providing an alternate pathway for the reaction to occur. And this other pathway has a lower activation energy. So if we're looking at the diagram of the potential energy as the reaction occurs, if there is a catalyst present, the bump, the energy hill, will be lower. But notice how the potential energy of the reactants and products is still the same, as well as the total change in energy. The only thing different is the activation energy. And we can classify catalysts into two groups, a homogeneous catalyst and a heterogeneous catalyst. And so the classification depends on if the catalyst is in the same phase as the reacting molecules. So for example, if we have a reaction with gas molecules and the catalyst is a solid, then they're in a different phase, and so the solid catalyst would be a heterogeneous catalyst. Whereas if the catalyst was a gas, same as the reactants, it would be homogeneous.